Okay, in this video we will be talking about the sampling distributions and the central limit theorem. So it has two parts. We will understand what are the sampling distributions, and then we will look at the central limit theorem. Before we do anything, I would like to tell you that this central limit theorem is considered to be the most important theorem in inferential statistics. Remember, inferential statistics is when you have a sample, and using the sample statistic, you infer something about the population parameter that you are investigating, like the mean or the standard deviation, and so on. This central limit theorem really lays the foundation of inferential statistics, so it's very important that you understand it. And this picture here is summarizes the central limit theorem. You will understand it by the end of this video for sure. So let's first I would like to say something. Try taking breaks during the video. I actually put some slides where I tell you to take a short break so that you can watch the entire video without getting tired or bored or something. So first thing I would like to talk about is something that is related to what's going on today. There is a YouTube video that is made by someone who calls his channel 3 Blue 1 Brown. He's a mathematician, and his channel actually has a high number of subscribers. He has 2.65 million subscribers, and the video that I want you to watch has been already viewed by almost 1,400,000 people. And imagine, it was published just 2 days ago, actually less than 2 days ago, about maybe 36 hours ago approximately this was published, and immediately look at how many people watched it. So I kind of trust the results that come from this video. This video is about simulating an epidemic. So in this one, he's not talking about coronavirus, the COVID-19 in particular. He's talking about epidemics in general. And he simulated this process and shows the dynamics of epidemics. Notice before we do anything is here the infections or the infectious people are put in red. The susceptible in blue, and the ones that are removed or recovered are the gray. So notice one thing. Do you see that this is approximately looks like a normal distribution? So this is actually very nice that you see normal distributions everywhere. And on the horizontal axis here, it's the number of days after infection. And the vertical axis is the number of people that are infected or susceptible or removed. You can check all of these things at once from this graph. This type of graph is called stratified graph, and you can look it up and read about it if you don't understand how to read this graph. But what's important is they put the infectious in the bottom, so you can see clearly that it's approximately a normal distribution. So there is another thing that he defines in his video. By the way, he is a mathematician, and his channel has a lot of nice videos. If you're interested in learning more mathematics, he simplifies things very well. Okay, so there is something here that we call R. He, of course, used a lot of different parameters when he was making this program and the simulation. And one of them is this R. R is a standard thing that people that work in infectious diseases must know it. This is called the reproduction number. So let's just write it, reproduction number. And this one is the ratio between two things. So this is the ratio between the number of expected infections that by a person divided by the number of people that are infected already, the number of already infected. Okay, so if you take this ratio, for example, if someone infected one person, okay, and then we are expecting that they will infect two more people, so you will do 2 over 1, which is 2. Okay, that's how it's calculated. Of course, the numbers could change, could be anything. Okay, so here is the link if you're interested. Also, I'll put the link in the description of this video. So let's go to the next page, and here I want you to understand some definitions. If this R, the reproduction number, is bigger than 1, so this picture, for example, is when it's 2. So a person infects one person, and we expect them to infect another one, and then each one is infecting 2 others. Each one is infecting 2 others. This is just a picture to show you that this will grow exponentially when R is bigger than 1. And in this case, we will call it an epidemic. Epidemic, okay? An epidemic becomes something called pandemic when this R is larger than 2. Like, let's say if R is bigger than or equal to 2, then it's an extreme case of an epidemic, so people usually refer to it as a pandemic. Okay, so if R is 1, you call it an endemic, and there is no name actually for R less than 1, but the maker of the video suggests that you call it hypodemic. Okay, hypo from weak or below. Okay, so that's about this R, the reproduction number. Okay, and also in Wikipedia, you can go to Wikipedia and read in epidemiology what's the difference between an endemic and an epidemic. You can read this, but since now we have the coronavirus, the COVID-19, it is an epidemic, and some people consider it even as an extreme epidemic, so they call it a pandemic. So it's an epidemic is the rapid spread of disease to a large number of people in a given population within a short period of time. This is what an epidemic is, and that's what he's simulating in his video. One pandemic that happened in between January 1918 until December 1920 is the Spanish flu, and the result of it was catastrophic. The confirmed cases were 500 million people, and the deaths that resulted were between 17 and 50 million. These are estimates. Okay, so this happened at a time when people didn't understand viruses and their dynamics and how to. They didn't even have antiviral drugs by then. They didn't have vaccines for certain viruses, and so this was a big catastrophe. Let's just look at the confirmed cases and the deaths and see what percentage of confirmed cases died with this Spanish flu. So we will go to the calculator, and remember, actually, let's put them together. That would make it easier to solve it. So here we have the deaths were 17 to 50 million. So let's say 17 million divided by the confirmed cases were 500 million. So divided by 500. Of course, because they're million, the zeros cancel, so you can just do it as 17 over 500. And so this is telling you that for 17, let me choose another color. Just 1 second. So let's do this. For 17, if you do the ratio to find how much is 17 over 500, it's about 3.4% of people who got it ended up dying, up to maximum. So this from here to 50. That's the maximum estimate that they have. And you'll get 0.1, which is 10%. Exactly, actually. So this is a very bad situation. So imagine 500 million people were infected with this and were confirmed, and 10% of them died because of it. But remember, as I told you, at the time they didn't understand viruses very well. In fact, if I remember correctly, the first virus that was discovered in 1890 something. Let me remember. I think I know it. 1892. Okay, and it was discovered by a Russian doctor. His name was Ivanovsky, or Dmitry Ivanovsky. I think it's written like this, but maybe I miswrote it. But imagine, 1892 was discovered, and then 1918, the Spanish flu happened. So it was not enough time for people to study viruses and things like that. But now in our time, we understand viruses much better, and we can deal with epidemics much better than before. So in his video, he actually had it into 6 parts. First, he puts the basic setup where he defines all the parameters that he's using in his simulation. Then he starts by the first thing that you do is when you identify and isolate the infected cases. Then social distancing. This is actually what I want to talk about from his video. And then travel restrictions. R is the one that I just told you about, and central hubs. Remember what was R? It was the reproduction number, and it was the number of expected infections that a person might give to others, divided by the number of people that are already infected by this person. Okay, and yeah, this is R. Travel restrictions, you understand what it means. Central hubs, he also puts this as a parameter that, you know, in every city you have malls and you have universities, schools. These are kind of like central hubs. Also train stations. It's a place in the center where a lot of people come to. Okay, so avoiding these places is crucial when you are fighting a pandemic. Okay, so now, as I told you, I'm going to only talk about in detail about the social distancing, because this is what people are doing now. Okay, so for social distancing, I told you before that blue means susceptible. Susceptible, by the way, it means that they can get easily infected. And infectious, it's a person who has the virus and can give it to others. Recovered are the people that recovered from the illness. Okay, so he also defined something that he called the social distance factor. First, he let his sample move in random walks. If you don't know what is a random walk, it's not important, but it It can model population dynamics very well. And the social distance factor, when you set it to 2, it means that when a person is 2 meters away from another person, if the distance between them is 2 meters or less, then they repel each other. They go away from each other. Okay? So he set it at 2 to make it reasonable. Okay? But you can play with what he did in the link that I will show you, and you can put it at 0 or at 5 and see what happens. Okay? So social distancing is very important. Now let me show you what he discovered when he was doing the simulation. He actually found that, of course, he set the social distance factor to 2 in all of these situations. And I want you to know what's the difference between the situations. Before you know the difference, notice that this is approximately normal. The curve is approximately normal. It's a bell-shaped curve. Okay? And when you have 100% of the population doing this social distancing, then you eradicate the epidemic much faster. So if you look here, let's zoom in. It looks like 15 or 14. Yeah, this 14 days to 15 days. This is the mean of the mean where you have the infected people. Okay, so it takes 15 days to, let's say, to show the symptoms. And if you look careful, you'll see that it ends almost before 25. So it's kind of telling you, like maybe 21, or where you find that it's almost 0, is, let's say, about here at 24. So this means that 24 days, like 3.5 weeks, if the population is 100% doing the social distancing, then the epidemic or pandemic in this case will go away very soon. Now, if instead 90% of the population or 70% of the population or 50% of the population do the social distancing, then it takes longer for the thing to go away. So here you see that even after 30, like this is 35, and it's still there are infected people. So it's really important. The lesson you take from this is that to eradicate a pandemic, one of the most important things is that 100% of the population is social distancing from each other. Okay? So after this, now if you want, you take a short break, drink coffee or meditate, do yoga, exercising. Try not to do like this. Try not to sleep, please. But even if you could sleep and wake up in 5 to 10 minutes, then it's okay. So, okay. Now I will, you can pause the video now, and I will continue in 3 seconds. Okay. So now we will talk about the sampling distribution. This is the first part of this lecture. The thing that I talked about simulating an epidemic, this is you're not responsible for, but because right now we have this thing, you know, we are home and we are staying home and we want to understand it better. So I really suggest that you watch the YouTube video. It will make you understand it better. And it's only about 23 minutes long. So when you have time, watch it. But don't watch it now. Just finish this lecture and then watch it, please. So sampling distribution. Here we first need to remember what is a statistic. Remember a statistic? This is any quantity that is calculated from sample data. So this is the definition. Let's even highlight it better. So this is what a statistic is. So like what? Like the mean. And remember for sample, the mean, we call it X bar. And for example, the variance, for a sample, we call it S squared. Standard deviation, also we call it S. And for example, this you're not responsible for, but there is something called proportion. You can compute it, it's called P hat. But I want you to, since this is something we are not going to look at, so forget it, but I want to remind you of one thing. Remember, X bar is for a sample. This is the sample mean. What is the population mean? How do we write it? Remember, we write it as mu. This is for population. And the variance, the population variance, we write it as sigma squared. And the population standard deviation, we call it sigma. Just remember these things for population. Okay, so let's say that this is your statistic. You have your sample mean. So what we have done now is we know what is a statistic. This is the what question. Whenever you want to understand the concept, the first question you ask is, what is it? Define it at least so that I can see if I can use it or not. Then, then the second kind, so this is the what question. And the second question you ask is the how question. How is when you are interested in how does it behave? How does this statistic that you just defined here as any quantity that is calculated from sample data, and I told you think of it from now as the sample mean, okay? So how does it behave? Now if you think of it as the sample mean, you know that it varies from sample to sample. So if you choose a sample of 15 people and you measure their heights and you take the average of that, then you take another sample of 15 people and you measure their heights, then you expect that the two average heights are not going to be exactly the same. So because this varies from sample to sample, it becomes a random variable. And it has a probability distribution, because every random variable has a probability distribution that we call the sampling distribution. So this is the definition of a sampling distribution. It's the probability distribution of the sample statistic. And in our lecture, this lecture, we will talk about the sample mean. We will do the sampling distribution of the sample mean. And now we know the answer to what, we know the answer to how it behaves, and the last question that you usually ask is why? Why bother study this statistic? Okay, read with me. The knowledge of the sampling distribution of a statistic, what does it do? It helps to make inference about the corresponding population parameter. So remember, what is a population parameter? It's the same definition as a statistic, but you just say any quantity that is calculated from population data. Okay, so as we said before, mu, sigma squared, or sigma, these are the population mean, variance, and standard deviation. Okay, and so the answer to why is that the answer is this sampling distribution of the mean of the samples is going to help us to get information about the population mean. So you go from the sample to the population. And remember, that is exactly what we called inferential statistics. Inferential statistics. Okay, good. So let's go to the next page. Okay, I'm going to just do it again, but in a different way. So a sampling distribution, remember, it was the probability distribution of a sample statistic. And I told you that for us, for this lecture, our sample statistic is going to be the sample mean. Okay, so we'll take it to be X bar. Okay, we will not study the sample statistic when it's, for example, the variance or standard deviation or range. All of these things can be studied also, but for this course we will do X bar. So that will be our sample statistic. Now, this sampling distribution is formed when samples of size n are repeatedly taken from a population. So it's important that the sample size is the same for all the samples that you take. So for example, if you decide to do an experiment where your sample size is 30, then all the samples that you take must have sample size 30. Okay? You cannot take a sample 30 people and then another sample 20, another sample 40. That's not allowed. When you decide on a number, that is the number that you should use for all the samples. Okay? And the most important example, and this is why we're doing this lecture, is we will study the sampling distribution of sample means. Okay? So it's kind of the average of the averages, or the mean of the means. That is the sampling distribution of sample means. You will see what I mean soon. Okay, just to remind you, the population mean, if you remember, it's calculated by this formula. Mu is calculated by adding all the data values in the population, and the population size is big N. Usually we write big letters for population and small letters, as you can see here, and here, okay, for sample. So remember, this is mu, and the one here is X bar, which is the sample mean. Okay, and so let's see the probability. Okay, in fact, I'm going to talk about what's written here. You can read it. Of course, the PDF of the lecture, you'll find it in the description of the video. And as I told you, better that you download it first, print it in color, and then have it with you and write on it with me. Okay, so I want to show you what is the process of sampling distribution. So let's say I'm going to choose, let's say, 5 names. Let's say that we have 5 females. Let's say the first one is Shamma. Okay, second one is Mona. Third one is Fatma or Fatima. Fourth one is Arwa. And the fifth one, let's say, is Uhud. Okay, so let's say that, of course, we want more, but each of them can do more samples also. So let's say that these 5 girls decided to do some survey on, let's say, the average age. They're interested to know the average age of people that live in the UAE. Okay? And before I show you what they will do, I want you to know something, that the population of the United Arab Emirates, as of March 28, 2020, so just yesterday, okay, it's 9,858,991. So we can say approximately 10 million. So that's the population of the UAE. You can also read other important things. It's nice to know the information here. I got it from this website here. So, and the link also will be in the description. It has other interesting facts about all the countries in the world. You can go by country, by continent, and of course the world. You can see information about all countries, and this is updated daily. Okay, so the 5 girls, or let's say the 5 students, know that the population of the UAE is like 10 million, and they want to know the average age. So are they going to ask the 10 million people to tell them their age? it's impossible for them. So what they will do is the following. They will all agree on a number. Let's say they agree on 30. So Shamma will, let's say, maybe call or send an email or put a post in any of the social media asking 30 people for their age. Once she gets her 30 data, which are the ages, she will find their mean, their sample mean, x1 bar. We're calling it, because it's sample 1, we're calling it x1 bar. Now for Muna will also need to find 30 people and ask them for their ages. Same for Fatma, same for Arwa, same for Uhud, and so on. Okay, and each one of them will call her average, her sample mean, x sub her number bar. So, for example, Arwa will call it x4 bar, Uhud x5 bar. Okay, I want the bar to look, because it must be there. So the sampling distribution consists of the values of the sample means. Now your sampling distribution is the distribution whose data values now are the means of the samples. Those are the numbers you're taking. Okay, now you're taking means as your data, sample means as your data. Okay, now what will you do? You will do their probability distribution. Okay. Now, there are two facts that are the most important facts on sampling distribution. So they are the properties of the sampling distribution. The first one is that if you take the mean of all the sample means, so remember in this example, what they will do is they will add all the means that they had for their samples, plus, let's say that they took how many? Let's say m bar, where m could be any number, could be 100 samples or 1,000 samples, and divide by the total number m. Let's make it look better. So wait a second. We will put just one line under them so you understand. You'll take this and divide it by their number m. So that is the mean of these means. And if you take all the possible samples of size m, then the mean of the sample means, we call it like this, the mean of the sample mean. Look, when you're reading it, you can write it, but you put it sub, this is mu sub x bar equals mu. This is a very nice fact that if you know the population mean already, even if you don't know it, the sample means eventually will get closer and closer to the population mean. And as your sample size increases, and as you take all the possible samples in your population, you will get this result, that the mean of the sample means is the population mean. And this has a name. It's called the unbiased property of the sample mean. It's important that you remember this definition here. The unbiased property of the sample mean, you just say it means that the mean of the sample means equals the population mean. And don't worry, you will understand it. Right now, maybe because the first time you hear it, you think it sounds difficult, but actually it's so simple. Once we reach exercises and examples, I will make sure that you understand this perfectly. So when you come back to this slide again, you will think of it as a very nice and simple slide. And the second property that is nice of the sampling distribution for sample means is that the standard deviation of the sample means, so you do the same as you did here, where you took the mean of the sample means. So here you'll take the standard deviation of the sample means. So this is equal to the population standard deviation sigma divided by the square root of the sample size. So if you remember for the 5 girls, we need more girls, but the 5 that I mentioned, they chose their sample size to be 30. So 30 is actually, we'll see that it's a good number, and in some sense you shouldn't take less than 30, except in just a few situations. So usually you take 30 or more as your sample size. Okay, remember, it's a magical number for us in this course, n equal 30. So, but for them, for them it was 30. So what we will do, what they will do is they will take the population standard deviation and divide it by radical 30. This is going to give them the standard deviation of the sampling distribution. Okay, this is very nice. Just 2 formulas to remember, these 2, the ones that you see here, that the mean of the sample means is the population mean, and the standard deviation of the sample means is the standard deviation of the population divided by the square root of the sample size. Okay, so let's go to this example now. In this example, I'm going to skip a lot of things because it asks you things that you already should know by now. It's from the early chapters in this course, from chapter 1 or 2. So the example goes like this. The population values 1357, so this is our population, so it's all what we have, are written on slips of paper and put in a box. So I'm giving you a visual thing here. So see a box, and it has 4 slips of paper, and each one has a number on it, 1, 3, 5, and 7. So what is the question? The question is that 2 slips of paper are randomly selected with replacement. So let's understand what this means. It means that you will put your hand inside the box and take 1. Okay, the probability that you'll get 3, of course, is what? It's 1 out of 4. Okay, and then you will, after you take it, this is the 3, you took it, so you return it back. That's why we're saying with replacement. You put it back and then you choose a second one. So that's what we will do. And you know, when you put back, you make the 2 events independent. That's nice to make things independent, because then the probability becomes easy. If you remember, if 2 events are independent, let's call them A and B, then the probability of A and B is just the multiplication of the 2 probabilities. Probability of A times probability of B. This is if A and B are independent. Okay, so it's a very nice property when they are independent. So anytime you do with replacement, it will give you independence. So this is good to know. Now, so our population size is 4. Why? Because we have 4 numbers in our population. And so let's read what the question wants. Find the mean, variance, and standard deviation of the population. That's part A. So at least the mean, you should tell me how to do it. Mu, the mean, is you add the numbers 1 plus 3 plus 5 plus 7, and you divide by how many we have, 4 numbers. So this is also, this is our big N, okay? And so you'll get 1 plus 3, 4 plus 5, 9 plus 7, 16 over 4, which is 4. So that's the mean. And on your calculator, you learned how to do variance and standard deviation. So if at this point you forgot how to do this, you do it yourself. You look back at the notes, older notes, or go online and search for a video that teaches you how to do it. I gave you a video in the past that does it, but just go on YouTube and type mean, variance, and standard deviation using, and then put the title of your calculator, the name of your calculator. Okay, so mu is 4. I'm going to show you quickly. Yeah, mu is 4. If you compute the variance, it's 5. And the standard deviation is radical 5. Notice that these are for the population. These are for the population, the mean, the variance, and standard deviation. Okay, now what is the second question? is, okay, let's do it this way. Now we are done with A, now we are in B. Graph the probability histogram for the population values. Let me ask you a question quickly. What is the probability that you will draw 1 on your when you take it outside, when you randomly select? I mean, the probability that you'll get 1 is just 1 over 4 or 0.25. What's the probability you'll get 3? Also 0.25, and so on and so on. Of course, they all have to add up to 1. And you can see it here. This is what we call a uniform distribution, because all of the values that we have, 1, 3, 5, and 7, have the same probability. So 0.25, 25%. So this is the probability histogram of the population that we have. Now, this is done. What is C? List all the possible samples of size n equal to, samples of size n equal to, all the possible ones, and calculate the mean of each sample. Okay, so now we will look at samples of size 2. So how do we do that? What we need to see is that, okay, you have the box. Let's do it here. I'm going to try to do it in this box. Okay, so our original box has 1, 2, I'll do it with rectangles or squares. 1, 2, 3, 4. And what are the possibilities that you can get if you want a sample of 2? Remember, it is with replacement. So I will do the tree diagram. How about that? So on your first draw, you can get one of the 4. You can get either 1 or 3 or 5. Oh, I'm sorry, or 7. Here I should have done this 1, 3, 5, 7. In fact, this should be 5 and this should be 7. Okay, 1, 3, 5, 7. This is what was given at the beginning. Look here. Yes. And now, this is the first draw. So let's write it in a different color. This is our first draw. Now, what about the second draw? So what will happen is that for each one of them, it should be combined with the other 4. Because on the second draw, you will also get 1, 3, 5, or 7. So the tree diagram will look something like this. So you'll put here 1, 3, 5, 7, 1, 3, 5, 7, and so on. Okay, and so what are all the possibilities now? Let's use this color. This one will give us, we need to decrease this. Okay, so this one is going to give us the possibility 1, 1. This one will give me the possibility 1, 3. This one is 1, 5. So getting 1 on the first draw, then 5 on the second. In fact, I should have said here that this is the second draw. Okay, and let's put this draw below the thing so it looks better. So draw. Okay, so and this one will give me 1, 7. And you can see I can do the same. And let's just do the last one. This would be 7, 1, 7, 3, 7, 5, and 7, 7. How many do I have? Each one is giving me 4. So 4 plus 4 plus 4 plus 4, or better, 4 times 4 is, you have 16 outcomes in here. So these are the samples of size 2. And calculate the mean of each sample. Oh, by the way, if they ask you calculate the mean of this sample, what's the mean of 1 and 1? You do 1 plus 1 divided by how many? Two values. So it will be 2 over 2, which is 1. The mean of 1 and 3 is 1 plus 3 over 2, which is 4 over 2, so it's 2. 1 and 5, you do 1 plus 5 over 2. That's the average of the 2, or the mean of the 2. So 6 over 2 is 3. And 1, 7, 1 plus 7 over 2 will give you 8 over 2, which is 4. So you see here, you got 1 as the mean, then 2, then 3 here, and then 4. Okay? For example, 7, 7, if you took 7, 7, you'll do 7 plus 7, 14 over 2, it will give you 7. 7 and 5, 12 over 2, 6. 7 and 3, 10 over 2, 5. 7 and 1, 8 over 2, 4. And you do this for all of them. And then we want indeed to construct a probability distribution of the sample means. So let's first finish C. I will show you the solution to C now. Look carefully at the picture. Okay, so it's exactly what I just did. I'm putting for you all the possible samples of size 2. So in this case, n equals 2, the sample size. Good. And the mean of each sample, I just showed you 1 plus 1 over 2, 1 plus 3 over 2, 1 plus 5 over 2, 1 plus 7 over 2. For example, this one, 5 plus 1, 6 over 2, 3. It will give me this 3. And so on. So, okay. So now look at the means here that you have. These are all the means of all the possible samples of size 2. Notice that you took all the possible samples. You took all the possible samples that you have, and that's why this is everything. There are no more samples of size 2 other than these. And we had 16 of them, remember? And so, okay, here, if you want to construct the probability distribution, remember, x bar 1, how many times did it appear? Let's just erase this part. How many times do you see 1? I see it 1 here, no more places. So 1 frequency is 1. Now for 2, how many times do you see 2 here? I see 1 and another one and nothing more. So 2 has 2. Let's do 3. 3, count how many times? 1, 2, 3. So 3 has 3. I'm not going to do all of them, but let's do 6. So let's do it with a different color. So 6. Let's count how many we have. We have 1 here and 1 here, and that's it. 2 6s. So 2. Okay, and this is how you do it. Then you find the probability. It's just the relative frequency. So remember, the total is 16. So for example, to get this number is the frequency divided by the total frequency. Remember, this is the total frequency. How many times it appears. Frequency is how many times it's repeated, the value. The total frequency is the sum of all the frequencies. You add all of these to get it. You know this already, but I like to review with you things that you studied in the past. So how do you get this number? It's just you divide the frequency by the total frequency. 3 divided by 16. And you can see here, 3 divided by 16 equals 0.1875. So correct. And the next question is, find the mean, variance, and standard deviation of the sampling distribution of the sample means. So here you will see, if you look at the numbers that I have here, so again we were going to, you can use either this or this here. You can use the frequencies, or if you want to just do it as ungrouped data, you will take all of these, and to compute the mean of the sampling distribution, you're going to add up all of these numbers and divide by 16, because we know we have 16 of them, and then you'll do 1 plus 2 plus 3 plus 4 plus 2 plus 3 plus ... and the last one plus 6 plus 7. Let's just, yeah, plus 6 plus 7 divided by 16. And if you do it, you will get 4. Notice, this is the same as the population mean. At the beginning, when we calculated the population mean, we also got 4. So this is reminding you of the first fact that I told you that you need to know, that the mean of the sample means is the population mean. Okay, and of course, the standard deviation has this formula. Another thing that I want to say that I forgot to say is that the standard deviation of the sample means, and let me choose green, so because we didn't choose it before, this has another name, and this other name is the standard error of the mean. So if you ever come across a question that tells you find the standard error of the mean, what they're talking about is the standard deviation of the sampling distribution, which it's very easy to compute. You take the population standard deviation and divide by the square root of the sample size. And remember that when we do sampling distributions, the sample size remains constant from sample to sample. So if you choose 30, you need to have all your samples 30. Choose 50, you have to have all your samples have size 50. Okay, and now we will see, yeah, if you compute the variance of the sampling distribution and the standard deviation, you know, you can do it on your calculator. You'll get these numbers. So mu x bar is 4. It's the same as the population mean. Now let's check. This mu x bar, sigma x bar, has this formula. And if you remember, what was sigma? The population standard deviation. It was radical 5. I will show you. Sigma is radical 5. You see it here. Okay, maybe highlight it. Okay, and you just use the formula. Divide sigma, which is radical 5, by the square root of the sample size, which is square root of 2. Because if you remember, we took 2 as n. So our sample size is 2. So that's why we divide by radical 2, and then we get approximately 1.581. And of course, it must agree with the calculation that we did when we used the values here. Okay, this is exactly what I told you that you need to remember always. So let's take away all of this. I just want to for you to see it clearly. The most important part of this lecture is remembering that the mean of the sampling of the sample means is the same as the population mean. And the standard deviation of the sample means is the standard deviation of the population divided by radical n. Notice that when you divide by radical n, usually n, of course, it's 2 or more. Okay, so you are dividing by a number bigger than 1. So this is always true, that sigma x bar is always less than sigma. So the standard error of the mean, which is sigma x bar, is always less than or equal to the population standard deviation. Okay, you will understand this when we solve examples. You'll understand it better. And the last question is graph the probability histogram for the sampling distribution of the sample means. And definitely here you can see that it approximates a normal distribution. This is actually the content of the central limit theorem that we will talk about soon. So this is an exercise that I want you to solve. So please now, from your PDF of the lecture that is in the description of the video, already I assume you printed it out. So please solve this exercise. It's very similar to the one that we solved here. Okay, I would say even kind of less things to do. Okay, but it requires you to do it for n equal 2, which we already did, but also for n equal 3 and compare when you take the samples of size 3. Okay, now time for a short break. I will start, pause the video, I'll start in 3 seconds. Okay, so now we look at the central limit theorem. As I told you, this is it forms the foundation for the inferential branch of statistics. This theorem describes the relationship between the sampling distribution of sample means, the one that we just were talking about, and the population that the samples are taken from. So it actually says something very simple to understand. It says that if you have, in fact, this is just number 1 is the central limit theorem. It's usually written as CLT. The central limit theorem says that if you have any population distribution, it could be skewed, it could be exponential, it could be uniform. No matter what your distribution is, if you take the distribution of sample means and you make sure that your sample size is at least 30, then the sampling distribution of sample means is going to be to be approximately normal. And because it's approximately normal, you can use everything that we learned about normal distributions in the previous 2 lectures. Okay, so it's very nice that you can get a normal distribution from any distribution once you take this sampling distribution of the sample means. Another thing that is not part of the central limit theorem, but I like to always put it next to it so you remember it, because it's very nice. It says that if you start already with a normal population, then you don't need to have this bigger than or equal to 30, at least 30 the sample size. If you take any n, any sample size, 2, 3, 4, those are all okay numbers, you will get an approximately normal distribution. So if you start with normal, definitely you'll get normal for any sample size n. But if you start with a population that is not normal, like this one, look, it has even 2 peaks. Yeah, if you start with something like this, then you need to make sure that the sample size is at least 30 in order for you to get an approximate normal distribution. Okay, so notice that something important. This slide is the same as what I said before, so I'm not going to talk a lot about it, but the greater the sample size, the better the approximation. So even though we asked for n to be bigger than or equal to 30, but really the more n is, so if you can do 50 people, it's better to take your sample to be 50 than 30. Or if you can do 100, it's better than 30. But 30 is the minimum that you should have if your original distribution was not normal. And if it is normal, again, this is not part of the central limit theorem, but it's nice to see it back to back or hand in hand with the central limit theorem. Then if it's already normal, any n is okay. And let's just for completion, n bigger than or equal to 30 if you have any population distribution. Okay, so I remind you again, if you have any population distribution and you start taking samples of size bigger than or equal to 30, then the resulting sampling distribution of the sample means will be approximately normal, with mean the same as the population mean mu and standard deviation equal the population standard deviation divided by the square root of the sample size. Okay, and the same thing here. The formulas are the same. So now maybe you're starting to feel that these formulas are important. Okay, and here this picture, look at it and see first we have the population shape. It's showing you something nice. If you start with a normal population, even if n is 2, you are getting normal. This is the sampling distribution here of the sample means. So if you take n equal 5, also normal. If you take 30, normal. This is nice. But if you start, for example, with a uniform population, then if you take n equals to 2, then it will look like this, like a triangular shape. N equal 5, it will start looking approximately normal, and n equal 30, this is where it's almost guaranteed. There are some situations where you need more than 30, but those probably are things that you will not see in this course. And the last one is if you have an exponential population like this, then if you take n equals to 2, you will get a shape that still is not normal. N equal 5, you'll get a shape that is still okay, but not normal. It's not bell-shaped exactly. And if n is 30, yes, now we see that it looks normal. That is what is this distribution here? It's the sampling distribution of the sample means in all of them. It's the sampling distribution of sample means that becomes normal as the sample size increases. And if you start with normal population, you are okay. Any sample size is fine. But if you have uniform, exponential, or skewed left, skewed right, then in this case you need to take your sample size at least 30. Okay. There is an online calculator that can model this for you and make several computations. In fact, I will just quickly show it to you here. Let's have it as a full page. So begin. The link is in the description of the video. So here, let's say you can start with normal or uniform or skewed. This one is skewed to what? It's skewed to the left. Okay? Sorry for this. Put it back, uniform, skewed. You see, it's skewed to the left because the mean, you see it here, the mean is 8.08 and the median is 7. So the mean is larger than the median. So, and you can see from looking at it that it's skewed to the left. Skewed to the right because the mean is higher than the median. Okay? And let's say you take a skewed one and then you want to take you want to do the sampling distribution of the mean. Notice you can do sampling of the median, sampling distribution of the standard deviation, and so on. But we are studying only sampling distributions of the mean. And here you can choose your sample size. So let's say I choose 25. Then you can animate here. If you see, it will animate by taking a random 25 sample from the population. So I'm going to click on animate, the one that you see here. Okay, and the animation will be from what I chose. I chose 25. Okay, so animate, count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. It will be 25, yeah, and it's taking it at random. And then after they get the 25, they give you the average of those 25 that they randomly select. And you can continue doing another animation, but I don't want to waste your time, so I'll do 5 more. So look at what it looks like. I will do fit normal, so you see that still I only took 6 samples. The 6 that you see here is how many samples you took. And notice that you can take 10,000 samples. You can do 5, 10,000, or 100,000. So let me jump quickly and do 10,000. So you have taken a lot of them. This gives you what looks like a normal distribution. So this is nice. You see, if you start with, let's say, uniform, and again, take your sample size. I will take it 25 again, and I want to, of course, do the sampling distribution of the mean. So at 10,000, immediately you see you get normal distribution. Whereas if let's clear it and animate, okay, animate this, that will give us 1 sample, and then below it will give us the mean of this sample. This blue one is the mean of the black ones up, and the black ones up are 25 people that are selected from this population. Okay, so let's add 5 more, 5 more, 5 more. See, keep on adding 5, 5, 5, 5. As your number of samples here, the 76, increases, you can see that you are getting approximately a normal distribution. See, as I'm adding, and look at the mean of the population. It's 16. You see the mean, the blue one is 16. What is the mean here? 16.04. So they are almost the same. And the standard deviation is 9.52. Here I have 2.52. So let me continue adding more samples. I'll add another 10,000 samples. Look, perfect. It looks like it's normal now. And I'll add one more. So let's see, we want to get 16 exactly. So I got 16 exactly. It doesn't matter. I took a lot of samples, I know. So I have the same mean as the population mean. This is what we learned. Mu x bar is the same as mu. And the standard deviation, we got 1.90, this SD, 1.90. And remember, our sample size is 25. So the standard deviation of the population is 9.52. So let's see. 9.52, let's do 9.52 divided by radical of the sample size 25 equal 1.904. Notice that the standard deviation, the red, is 1.90. So very simple. Okay, good that we checked it. And you can play with this calculator and see animations and so on. But that will be it for me, at least, for using this. Now you can look at these two things. One of them is when you start with any distribution, then you apply the central limit. I mean, you see the central limit theorem in action. Okay, and I'm showing you three examples where I change here. The n is 25, sample size 25, sample size 16, sample size 5. Okay, and the same here for the sample sizes. But because we started already with normal, then we expect that we will get all of them normal, no matter what the sample size is. Okay, there is only one thing here that I didn't mention, is that if distribution is fairly symmetric, if you look at it and it looks symmetric, then you can actually use n bigger than 15. You don't need 30. Okay, in some cases. And please read the other bullet points. You will learn something from them. But most of the stuff that's written here, I already said it. Last thing is how to go between x bar and z. So now that we know that x bar follows a normal distribution with mean mu x bar and variance sigma x bar squared, okay, which is the same as saying normal with mean mu, because mu x bar is the same as mu, and variance sigma squared over radical n. In fact, better to write it like this over this squared. So you remember that what you see here is just the standard deviation of the sampling distribution. Okay. Remember, this is what I mean to say is mu x bar is mu and sigma x bar is sigma over radical n. I'm more interested in the mean and the standard deviations. The variance, not that much now. Okay. So you use the same formula that you used before. Remember Z? Before, what did we do? It's the data value minus mu, the population mean, over the standard deviation. Now, all what happens is that you're taking another distribution, that is the sampling distribution of sample means. So you just add the x bar, okay? And mu x bar is the same as mu, and sigma x bar is the same as sigma over root n. And to go back from from z to x bar, so if you are given z and you need x bar, this is the formula. It's just the inverse of the formula here, just like what we did for normal distribution. Okay, now you can take a short break and come back to the last part. Okay, so our first example is this one. An electrical firm manufactures light bulbs that have a length of life that is normally distributed. This is nice to know, normally distributed, with mean equal to 800 hours and the standard deviation of 40 hours. So mean is 800 hours, standard deviation is 40 hours. So I will write this as mu. This is for the population. Let's see. Yeah, it's for the population. Mu is 800 hours. Now, 800 hours is approximately 33 days. And sigma, the standard deviation, is 40 hours. So, like what, a day and a half or something? Yeah, or just a little bit above 1.5 days. Okay, and what is our random variable x? X is here, what is the thing that is normally distributed? You see, an electrical firm manufactures light bulbs that have a length of life that is normally distributed. So this is the lifespan or length of life of the light bulb, even without writing light bulb, of this thing here. Okay, and let's see what the question is asking. Find the probability that a random sample of 16 bulbs will have an average life of less than 775 hours. I want you to see how easy this is. Okay, so for us here, the sample has, our sample size n is 16. So since our distribution is normal already, it doesn't matter what the sample size is. So this will, to apply the central limit theorem. So this means that sigma x bar is going to be sigma over root n. And so what is sigma? It's 40 over radical n is 16. So I don't need a calculator for this because radical 16 is 4. And so this will be 10 hours. Okay, good that we know sigma x bar. Also, what is mu x bar? Mu x bar is the same as mu, and so it is 800 hours. So let us now find, what we need to find is the probability that, read carefully, the probability that a random variable of 16 bulb will have an average life span of less than 775. Average life. So we want the mean to be less than 775. Okay? And so in order to calculate this, all what you need is to remember that n is 16. Well, n is 16 already. We took care of it by writing what is sigma x bar, which is 10, and what is mu x bar, which is 800. So all what you need to do now is go online to the calculator that we have, and here we need what we need area from a value. The value is 775. So all what you have to do now is put the mean. What is our mean here? It's mu x bar, so it's 800. So you put 800, and the standard deviation, of course, you're going to put this here, 10 hours. You're not going to use the 40 hours. Okay, never do that, because this sigma is for the population. But what the distribution you're working with now is the sampling distribution, because you took a sample of size 16. Okay, remember this. So you'll put 10 for the standard deviation, and you need the area below 775. So below 775, and calculate. So what we're getting is 0.0062 approximately, which is 0.62%, less than 1%. The probability that if you take a sample of 16 bulbs, they will have an average life less than 775 hours. Notice that this is exactly the same as what we've done before. You just have to enter the right mu and the right sigma. Now the second question is find an interval symmetrically distributed around the population mean lifetime that will include 95% of the sample means based on samples of 16 bulbs. So we're still using 16. So what we need is the mean is here, the 800. This is mu x bar, and you want a 95% area. Okay, so you want to find the lower and the upper bounds here for 95%. So you will assume that this area is 0.95, and you're asked to find the value here and the value here. So this is, you can call this lower x bar, and this is upper x bar. And let's see how to find it. Now you need value from an area because you're computing xl bar and xu bar. So the area is 0.95 between them. Remember, the mean was 800 and the standard deviation was 10. And so we want between. So calculate, yeah. So now we know that the smaller value is 780.4 hours. And the second one is 819.6 hours, or 820 hours. You can say 780 and 820, between 780 and 820. So this means that 95% of your 95% will be between 780.4 and 819.6. Okay, I actually prepared something for you to watch on light bulbs in general, and I like to add these things to my videos so that you learn something from watching. Please read these. When you download the PDF, read it, it will teach you something. It's good to always know something additional. For example, when you read that the problem is about light bulbs, why not look up how do they really do the experiment to measure the life or average life of a light bulb. It's all written here clearly, so please read it. The solution is given here also using the classical method, but since we have the online calculator, we did it quickly. All what's important were these two things, as you remember. Okay, so now we will go to the second question, second example, and we will solve it quickly. The amount of time a bank teller spends with each customer has a population mean. So population mean mu equal 3.10 minutes and a standard deviation sigma equal 0.40 minutes. Okay, good. If you select a random sample of 64 customers, let me just put a line under the important things. So sample of 64 customers. So here my sample size is 64. Notice that here they didn't tell us anything about the distribution being normal or not. So you suspect that it's not normal, or you don't know if it's normal or not. So if it's not written, do not assume it's normal. Okay? So, but the fact that we took 64, that's more than 30. Remember, it was 30 was the number that you take when you have any distribution. The sample size of your samples should be 30 or above to get the sampling distribution to be approximately normal. So since it's 64, central limit theorem works. Okay? And the question is, what is the probability that the mean time spent per customer is at least 3 minutes? So what's the probability that the mean time, that's x bar, the average time x bar, is at least 3 minutes? So more than or equal to 3 minutes is what? That's the question. So before we solve it, we need to know what is the mean of the sample means. So mu x bar is the same as mu. This is 3.10. So immediately you get this easy fact that the mean of the sample means is the population mean. And the second nice fact is that the standard deviation of the sampling distribution is the population standard deviation divided by the square root of the sample size. So sigma is given to be 0.40 divided by radical 64. And we know that radical 64 is 8, because 8 times 8 is 64. And now if you divide 0.40 by 8, you will get 0.05. You can check on your calculator. That is what? Minutes, of course. So 5 of 100 of a minute. And this is 3.1, of course, minutes. So now all what you have to do is go to the online calculator. So let's see, yeah, here. And we need what? This is what we need. So actually, I need to do something here. First, just remind you that this is what we're working on now. This here, this is what we want to fill. Okay? And so, let's take away minutes from here. You understand that it's minutes, or I will write it here, minutes. Okay? And let's see. Now you want what? You have a value and you want an area or a probability. So you say area from a value. We still have the 800. That's not 800, sorry. This one is a different question. 3.10. 3.10. That is the mean of the sampling distribution of the sample means, and the standard deviation of the sample means, or we call it the standard error of the mean, is 0.05. So I'll put here 0.05 or 5%. And we want what? The area above, because this is x bar bigger than or equal to 3. So we want above. If you want to delete this, delete it, but it will not affect it. If you just click on above, it doesn't matter if you have other values that you entered before. So we want what? Above 3 minutes. So I want above 3. And so I'll say calculate. So put the answer. It's 0.9772. Okay, this is the answer, which is 97.72%. That what? This is the probability that the mean time spent per customer is at least 3 minutes for 64 customers. Our sample has 64 customers, and the probability that the mean time that is spent per customer is at least 3 minutes, or we can say 3 minutes or more, is very high, 97.72%. Okay, so after this, the solution also is given here. You can see we got the right answer. And of course, it's always important to remember to put this at the beginning when you're solving the question. Once you see that you're taking a sample and you're computing sample means, you know that you will have to do mu x bar. Your sampling distribution has mean mu x bar and standard deviation sigma over radical n. Remember that this was sigma over radical n, and sigma was 0.4. It was given at the beginning, 0.4 here. Okay, and you get the right answer. Here it's also solved by the classical method, changing to Z and do it. But because we have the online calculator, you can enter these immediately as the mean and standard deviation of our distribution, and then just put x bar bigger than 3. So we jumped just to this immediately using the calculator. That's why it's nice. Now, last thing is the homework. So I have taken 4 exercises that were prepared by Dr. Rafiq Hijazi. So we thank him again for his help. Most of the slides that you saw today, 50% of the slides that you saw today, he made them already. Okay, so please do the same as the previous lectures. Download the PDF of the exercises, solve them, and send me your solution. And don't forget to always put the picture of the answer. So take a screenshot of this when you're answering and attach it, showing me the answer, and always please include the distribution itself, what it looks like, the shaded region. I want to make sure that you did it correctly. Okay? And if you want to just work immediately, just take a screenshot now of this. So 1, 2, 3, 1, 2, 3. Okay, good. So now I will, last thing is, please, if you like this video, if you liked it and you think that it helped you, please like it on YouTube, and do not forget to subscribe, and also put the notifications on. And thank you very much for watching, and the next lecture will be solving exercises from this lecture. Okay? Thank you very much for your time, and take care.